I am Renzo Tao from Columbia University. I represent our work, Giallar, push-button verification for the Qiskit quantum compiler. Qiskit is the most widely used quantum computing platform, with more than 200,000 users and billions of circuit experiments run on it every day. It has been applied to various fields, including chemistry, finance, and machine learning. The Qiskit Compiler is a key component in Qiskit. It compiles quantum programs to quantum circuits that are runnable on a real quantum computer. Like many other compilers, Qiskit has bugs. These bugs may corrupt the billions of experiment results on the platform, causing huge scientific and financial loss. For example, this single bug that incorrectly merged the 2-qubit gates can put over 100 billion circuit experiments on the thread. Manually reviewing and debugging the compiler code are not scalable and require extensive knowledge of quantum mechanics, which is hard for a compiler developer. Testing can also be used to find and eliminate compiler bugs. But testing has no correctness guarantee, and Qiskit is already well tested and still have bugs. One may consider to use a proof assistant to manually prove that the compiler is correct. But it requires heavy manual work. For example, the Vox verified quantum optimizer uses 2,700 lines of code to verify the qubit mapping compilation path with only 70 lines of code. Moreover, manual verification cannot keep up with the rapid development of the constantly updated Qiskit. To overcome these limitations, we propose Giallar, the first automated verification toolkit for the Qiskit quantum compiler. Giallar is a push-button verification framework, meaning that it requires no manual annotations, invariants, specifications, or proofs. This avoids the high overhead of doing manual proofs and can keep up with the pace of rapid Qiskit compiler development. Using Giallar, we verified 44 out of 56 Qiskit compilation passes across 14 versions, while the other 12 passes are hard to prove, even manually. During the verification, we have found 3 bugs confirmed by Qiskit developers. And our experiment shows that the verified version has a similar performance to unverified Qiskit. Then the question is how to enable push-button verification on a quantum compiler. It presents unique challenges both classically and quantumly. First, symbolic execution cannot handle unbounded loops, which are essential for quantum compilers to traverse arbitrarily long quantum circuits. Previous push-button verification frameworks either only consider bounded loops or require user manually providing a loop invariant, defeating the purpose of push-button verification. It is also hard for users to correctly provide specification for different types of compilation passes. As for the quantum challenge, an n-qubit quantum circuit requires a 2 to the n times 2 to the n matrix to represent. Thus, automatically verifying a quantum compiler involves checking the equivalence of exponentially large matrices. Moreover, it is even harder to prove equivalence for an arbitrary input quantum circuit. To overcome these challenges, Giallar leverages domain-specific knowledge of quantum compilation. First, Giallar offers 3 loop templates where loop invariants can be automatically inferred. Giallar also provides a set of base classes for different types of compilation passes to automatically generate specifications. To deal with quantum states that require exponential size matrices to represent, instead of directly using matrices, Giallar treats quantum circuits symbolically and deduces equivalences using a set of rewrite rules. Here is the workflow for a Qiskit developer using Giallar. Developers first write a compilation path using Giallar. Then they specify the base class for the type of the compiler path. Giallar will preprocess the code into multiple pieces of sequential symbolically executable code, expanding all branch statements. During this step, Giallar also generates loop invariants using the loop templates. Then Giallar will use the Z3 SMT solver to symbolically execute the compiler code and generate verification conditions. In Z3, we define a set of rewrite rules that have been statically verified in the matrix representation for quantum circuits. With the help of these rewrite rules, Z3 will determine whether the compiler path preserves the semantics of the quantum circuit. The verified path can directly link with the Qiskit library and runs as a Euro Python program. To look at the verification process in more detail, let's look at the CX cancellation optimization path as an example. The CX cancellation path will find all places of the circuit where 2 adjacent CX gates act on the same pair of qubits and cancel the gate. We can easily write down this code that iteratively checks whether a gate is a CX gate, and if it is CX gate, and the next gate is also the same CX gate acting on the same pair of qubits, then both gates are removed. To verify the correctness of this optimization path, Giallar will get the specification defined by the base class and prove that the input circuit and the output circuit are equivalent. First, each conditional branch of the compiler code is unrolled, producing different execution paths through that compiler code. The conditions of those unrolled if statements are given to the SMT solver as assumptions. Though this will produce an exponential blowup of execution path in general, we have found that Qiskit compiler passes produces at most 8 execution paths. In the CX cancellation example, there are 3 execution passes. The gate is CX and cancelled. The gate is CX and not cancelled. And the gate is not CX. The unrolled code for the first branch will become this piece of sequential code on the left, with the condition added as assumptions in the SMT solver. Giallar will match all loop statements with loop templates and automatically generate loop invariants. Giallar provides 3 loop templates. Each defines a shape of the loop invariants with placeholder variables. Giallar will automatically fill the variables according to the given compiler code. For example, the while gate remaining loop template captures the loop that maintains a list of remaining gates and uses a while loop to scan the list and builds an output circuit. The shape of the environment is that the semantics of the currently built output circuit, together with the remaining gates, is equivalent to the input circuit, with 3 placeholder variables: the currently built output circuit, the remaining gate list, and the input circuit. In the CX cancellation path, the loop is matched to this template, and Giallar will find suitable variables in the code to fill the placeholder variables. Then, the loop environment will be given to the SM solver as a proof goal. Finally, the proof goals are checked by the Z3 SMT solver. However, if we directly use the matrix semantics, the cost will be exponential because of the exponential size matrices. Instead, Giallar represents the result of applying a quantum circuit symbolically, which supports scalable reasoning of an arbitrarily sized quantum circuit. To efficiently check the equivalence of the symbolic execution quantum circuits, Giallar introduces a set of 20 rules for reducing and rewriting gates, and these are part of them. The results are defined in symbolic terms in Z3. For example, the rewrite rule used in the CX cancellation path that the 2 adjacent CX gates on the same pair of qubits can cancel out is defined as these symbolic equivalence rules in Z3. The symbolic execution of quantum circuits and the rewrite rules are verified using the Coq proof assistant. Now let's show how to use the symbolic execution of quantum circuits and the rewrite rules to perform verification. This is unrolled symbolically executable code. And Z3 is asked to prove that the execution of the code on the left keeps this invariant. We represent the quantum circuit symbolically and generate the precondition P1 that the invariant holds before the execution, and the goal G1 that the invariant holds after the execution. Then, from the symbolically executable code, we will have a series of further preconditions which can help us simplify the goal. For example, we know that the variable output is unchanged by the code. Thus, we only need to prove the equivalence between the new and the old remain. We also know that the old remain has 2 more CX gates than the new remain, which leads to the simplified goal G3. We can further simplify the goal into G4 by symbolic execution and canceling C2. We also have the condition about the next variable, that the CX gate in the middle can be swapped to the beginning of the circuit. Finally, we have the rewrite rules that 2 CX gates on the same pair of qubits can cancel out. With all the conditions, Z3 is able to prove that the goal G4 always holds, verifying the correctness of the whole compilation path. We use Giallar to prove 44 out of 56 compilation passes in Qiskit across 14 versions, from Qiskit 0.19 to 0.32. All verification processes complete in 1 minute. Among all 12 unverified passes, 2 of them invoke external servers that are hard to specify. 8 of them involves pulse-level hardware features that have a lower level than circuit abstraction. 1 of them is approximate and do not keep the semantics of the input circuit. And 1 of them invokes a complicated randomized procedure. All 12 are hard to prove, even manually. During verification, we find 3 bugs in Qiskit, which we confirmed with Qiskit developers. 2 of them are quantum specific. We also compare the performance of the compiler passes verified in Giallar with the unverified version in Qiskit. The result shows that Giallar has a similar compilation performance as unverified Qiskit. Thanks for listening, and I'm happy to answer any questions.
Hi, thanks for the nice talk. I have a clarification question. So is the code that you're verifying the original implementation of the optimization, or is it a rewritten version that may be very different from what Qiskit has actually implemented?
Yeah, well, what we verify is a retrofitted version of Qiskit.
So how difficult would it be to apply something like this to the original Qiskit implementation?
I think it will be hard. It's like the original Qiskit implementation used a lot of like external libraries and something, and we basically want to be independent of that.
All right, thanks.
So one of the advantages of a system like Vox is that it has a relatively small trusted base, right, which is just Coq itself. And I was wondering if you could comment on how large the trusted base would be for the Giallar system.
Yeah. So the trusting computing base. So we have the Z3 SMT solver, and also we need to have the trusted equivalence between the Python the data structure defined in Python, and also the equivalence between the data structure in Python and the data structure defined in Z3.
Thanks. Yeah, I'm just wondering what is the boundary or kind of, so what kind of transformation are kind of allowed or considered in this framework? For example, can your tool be used to kind of verify the super optimization tool, like from the last talk, something like that?
Yeah. So let's go to that. So basically, our verification is like based on a set of rewrite rules, which is kind of like some small pieces of like circuit equivalence, and the super optimization is also based on like small set of like things. So right, I think it's kind of can be completely used together. Yeah.
Right. Again, so can it be used to verify the super optimization tool, like from the last talk? I forgot the name, but like we just presented like from the last talk. That one use some equivalent circuit and random testing and an SMT solver. That one, can that kind of thing be verified within your framework or be extended?
Yeah, I think so. It's like we can use like quotes to search for like pieces of like circuit equivalence, and also then we can also like use classical symbolic execution to verify the how to apply those rules.
Okay, thanks.
There was one more question. All right.
Well, I remember you said there are 3 types of template of loops. So, for example, if a Qiskit implement a new pass, and so is it possible that it contains a new kind of loop, and you cannot handle it, or is 3 kinds complete in terms of loops?
In principle, yes, it's like you can always like write any complicated loop. But our loop template is already very generous. Like there are for loop and also while loop, and like we have like different types of while loops.
Okay, thanks.